Okay, good morning. My name is Utkarsh Misra. I'm a PhD student here at UT. So today I'll be talking a little bit about strain-switched magnetic tunnel junctions. It was a good topic. I was going back and forth about a couple things, and I ended up working with one of our lab mates and trying to look a bit more into what strain-switched magnetic tunnel junctions are. So I'm very excited to talk about this today. So, quick table of contents. We'll just go over what is an MTJ, why should we care about strain, in particular, some experimental evidence that was worked in our lab with previous PhD students, and then some simulations that I ran, and some cool experiments, which I feel are fun to look at. So, what is an MTJ? So I think we briefly discussed about this in class as well. So an MTJ is a magnetic tunnel junction, which what it actually means is this is how an MTJ cell looks like. You have a free layer, you have a pinned layer, and then you have a tunnel barrier in the middle, and then obviously you have your readout circuitry around it. As the name suggests, your free layer is what has its magnetization switch around based on external factors, and then to an anti-parallel or a parallel state, and our reference is our pinned layer in the stack is the pin layer is our reference for the magnetization. So as you can see there, it's in an anti-parallel setup where the resistance that is read through the stack is the anti-parallel resistance, and then when it is switched into a parallel state, this is then the parallel resistance, and then these two resistances are not the same, and that's how you can electrically read out the two differences between these states. So basically, an MTJ cell will provide you ideally two different electric resistive states. And there's different ways to write these memory currently, or more traditionally, these have been written using current, and we'll discuss in a second why that current is a problem, and why we want to move towards something more strain and all this fun stuff. So why is MTJ really cool and is really important? And the reason why it is really important is because it brings together three most bright and three most important features of devices and in the device field together. It basically provides you a voltage-based writing. It provides you non-volatile magnetic storage, which is also very desired. And then on top of it, you get electrical resistive readout, which is the most basic form of readout. So putting these all together, this makes this device very interesting to work with. So what are the issues? So the issues, going the other way. So the issue is currently all the MTJs basically are switched with current. So you apply current, which basically affects the free layer and switches it. But if you can think about it, this is good for one device. When you have a lot of devices in an array, it starts causing problems. It creates joule heating. It has a higher write energy, and then you also have precision limits. So to move away from the traditional writing style, there's a strain-based writing style where you use piezoelectric materials. So if you guys don't know what piezoelectric materials is, those are materials where you apply voltage, they expand or contract. So when you combine them with an MTJ, they apply strain on MTJ, and strain then causes switching of the material, which is called magnetostriction. So the strain then offers a low voltage and potentially ultra-fast switching. So that's what we're looking into, what kind of times we can get with these switching, and what kind of voltages are required for this piezoelectric material. So with this, there were experimental evidence needed. So before this, there were thoughts about there are materials that you can switch their magnetization based on applied strain, but there were no thoughts about there were not enough literature and experiments and research about if this will ever work in MTJs. So some previous work from our group, which I got a chance to read while doing a literature review for this work, was basically using this FEGA material integrated into this MTJ stack, and showing that these high magnetostriction materials could be used for switching in an MTJ device setup. So this gives us an idea that on a device level, these things are realistic, and we are able to use these for devices. So based on that, I was thinking about how I can use simulations to show some of this switching behavior. So basically, what happens in a switching and when this device switches is you have different energies and different anisotropies fighting against each other, and then you apply strain that pretty much destabilizes the EZ axis, your magnetization from EZ axis, and then it flips on the other side. So what we can think of it as something that we've worked in class is you have an EZ axis. And your strain is pretty much providing a torque on your magnetic, dipoles, and then that they pretty much switch around on the EZ axis. So, well, for this, what I did was I chose a material terphenol D, which is a high magnetostrict. It's a material with high magnetostriction. That means when applied strain, its anisotropy is highly affected by the applied strain. It preserves TMR, which is important for reading, the resistive reading of the material. And then for the shape choices, I was going around with a couple different shapes, but I feel that the rectangular slab is our old trusty for all of our class simulations, so I just kept with that, as this was familiar, and then we really know the shape anisotropy of this material, so of this geometry. So so based on that, let's see if this simulation would work here. But what's going on here is different strain values. So strain is in percentage. That pretty much means that what percentage of the initial length is stretched or expanded. So 0.1% means of the initial length, 0.1% strain is expanded. And if we keep the angle between your shape anisotropy and the applied strain as same as 15 degrees, you can see as we increase the strain, if you just apply for, say, 0.5% strain, we see the magnetization is in Y. It gets a little push towards negative Y, but then it's not enough, so it kind of comes back and stabilizes on the initial Y-axis. But when we increase the strain, we see at around this sweet spot about 0.1% for this geometry and device, we see a nice -1 to a +1 switch. That means it's the magnetization starts aligned on the negative y-axis, and then as the strain is applied, it gives just enough torque for it to turn around and get to the positive y-axis. And if you apply too much strain, which is up here, which is 0.35%, 0.35% is terphenol D's fracture strain. So that's the maximum strain you can apply before the material fractures. And if you apply that much strain, 0.35%, that causes this dipole to pretty much just keep spinning, and it make this this GIF. I don't know if I can load it again, but yeah, if you see here, it will start once the strain is applied, it starts spinning, which I think was a fun experiment to see, fun simulation result to see from this this kind of setup. And based on that, so as we can see, different strain values cause different different effects of spin. So what I did was I tried to also vary angles. So if you can think about in our class demonstrations, we saw that different angles between these anisotropies and forces cause different amount of change because there's a sine component to it. So I varied some of the angles as well as actually there should be 25 degrees here, but from a 15-degree, 25 degrees and 45 degrees, and then you can see at different strain values they also switch. So so these are the so these are, showing that that as the angle changes, these devices, the strain MTJs, are also very sensitive to the shape and the angle at which the strain is being applied. So since this is an easy enough setup mathematically, we can also calculate all the different forces and the sweet spot angle. So simulations are due by Wednesday, so this is some ongoing work. I'm currently trying to put together some math and see if I can mathematically show the sweet spot for these strains and angles, but those are the simulation results. And yeah, I think that ends the presentation. From my experience, these are very cool devices, and this is upcoming field with strain, and I think it will have some challenges about integrating in a lot of devices and in a lot of material properties like roughness and different kind of material interfaces. But I think it overall, props are a great problem and field to be studied. So thank you.